Hello, I'm Professor Hussein Al-Huwaizi. Today I'm going to talk to you about a lecture entitled Preventing Fracture of Rotary Instruments in Endodontics. This is really very important because nowadays nearly everyone is using rotary instruments. I'm the chairman of the scientific committee in the Iraqi Dental Association, a professor in the College of Dentistry, University of Baghdad, coordinator of the Iraqi Endodontic Society, and member in many. This is my college. I work here. It's the Mother College of Dentistry in Iraq, and it was founded in 1953. Now, in the market, there are so many systems for rotary instruments. There are so many, so that really we don't know which one to choose. In order to understand the importance of this topic, I entered the PubMed and wrote fractured rotary files and found that there are 234 articles talking about how to manage the fractured rotary files. But I was very curious to ask how many articles addressed preventing fractures. To my surprise, there were only 12. So that means really we have to consider thinking about how to prevent rather than how to remove fractured instruments. First of all, we have to talk about certain literature. All rotary instruments are made from nickel titanium alloy. Now, this alloy, it's a super elastic shape memory metallic alloy. When flexed, it undergoes martinistic transformation from its original authentic structure. So this is a transformation here. You heat it, it becomes austenite. You cool it, it becomes martensite. If stressed beyond its elastic limit, it will fracture. During root canal preparation, night-eye rotary instruments are subjected to cyclic fatigue. That happens mostly in curved canals. Any file that entering to the curved canal, it will here be flexed more than. Now, talking about the tooth and its anatomy, we've got many curvatures. In the coronal third of the root canal and midway in the middle third, and sometimes even in the apical third. So in this case, we have to utilize this super elastic shape memory effect of the positions of fractures that may happen. They may be in the coronal region or in the apical region. All of these fractures, they happen because the alloy is there's a lot of stress on the alloy and then it fractures. That's why it's important for us to understand this alloy and understand our anatomy so that we do not exert a lot of tension on the file so that it fractures. Now, there are two main causes of breakage of rotary night-eye. First of all is cyclic fatigue. This area the file is going to be rotating, and it flexes until fracture. Usually the file fractures at the point of maximum flexure, which means the most curved area in the root canal. Torsional stress, this happens when the file enters down and it gets locked. The tip of the file gets locked or bound within the canal. It always happens in the apical region. Here, this tip is locked and the shaft it continues to rotate and it will fracture here. This is one example of such a thing. You can see that the operator did not widen the coronal third of the root canal so that he can get to the apical region. He went down straight away with a narrow canal, or maybe very narrow canal with an instrument, and here the instrument was locked in this region, and the other part of the file used to rotate, and it fractured here. This is a study by Eleanor. He studied the stress analysis at the curvature, different curvatures in the root canal with ANSYS, a way of showing the maximum stress that may happen. And you can see here at the curvature here, this area has maximum curvature. This is the red area. This is what we call cyclic fatigue. But with torsional failure, when there's a lot of stress in the apical region, in the tip, here, this area becomes locked and a lot of stress is here, and the stress graduates and decreases as we go coronally. Here, the file, if it stays locked in this region, it will fracture here. So it's important that no stress is made on the file as much as possible in this region and in this region. Tips to prevent fracture. First of all, we talk about the instrument design. Now, the size, taper, and cutting flute depths are very important factors that affect the torsional properties. First of all, when we talk about the size, literature is very controversial. Some say that the large instrument is susceptible to fatigue failure more than the small, and some say that the smaller instruments are more prone to fracture because they don't have a lot of metal body to withstand the forces. Either way, we have to be careful when using the instrument and not make it exert a lot of stress on the instrument. Taper, it is said by Shen et al. In 2006 that 20% of the progressively tapered instruments, for example, the ProTaper Universal or Next, they fail rapidly more than the constantly tapering, which is about 7%. Now, this increase in taper, what happens is that the more you increase the taper of the instrument, the more it will need a lot of torque to cut during rotation, and this will make the fracture time decrease. Now this is a video. It shows to us when I have got an instrument that works of a given taper that works in one area, just one area, that means the whole torque, the whole energy that's made by this file here, it's going to be concentrated in one area only, and here we will have the less fracture to the file. For example, this is the primary file of the wave 1. We take the working length. You can see here as it enters in the coronal region of the root canal, it widens the canal. You can see here that only this area has got debris. That means the apical region is not cutting. As the coronal region has widened, it enters even further, and now it cuts here, and this is very free or very little cutting. You can see the debris is more widened, and then we go to the apical region. That means sequential entrance of the file to the apical region is mandatory for the instrument to cut safely. Now, cutting flute depth is very, very important, because the cutting flute depth, if it becomes very deep, that means I've got many cross sections, narrow cross section and wide cross section. Now, if the narrow cross section is very narrow in relation to the wide, in this case, the stress that will be impinged on the file will not be distributed very uniformly, and it will concentrate in the narrow area. Therefore, there will be a lot of fracture. This is another study whereby they studied the cutting edge and its effect on stress distribution. This is the pro-taper universal type. The cutting edge is neutral cutting edge. You can see that the stress is mild between blue and green, which are very little. But when using the radial land, for example, the profile system or the GT system, we can see that there is a lot of stress that happens in the red region. Why? Because here we have cutting, and here we've got scraping. The more you scrape, it's just like scraping the wall with sandpaper, you generate heat. This heat will make a lot of stress on the instrument, and the instrument will fracture. That's why cutting is better than scraping. The motion of instruments movement, here we've got rotation and reciprocation. Reciprocation is 150 counterclockwise and 30 degrees clockwise. We can see here what is reciprocation. This is again the wave 1. We can see that there is counterclockwise and clockwise motion of the instrument. We can see here by ANSYS that when I do rotation to a file, we exert a lot of tension on the instrument, as we can see here, while with the reciprocation, you can see that the tension is much less. Why? Because now with reciprocation, my cutting phase is the counterclockwise. But after that, I've got a clockwise relief, which is 30 degrees. This relief phase decreases the stress on the instrument. That's why you will have the instrument, it stays for a longer time while working with reciprocation. Strengthening of the file, you can see that this is a close-up of a file whereby I've got certain serrations here. If we magnify it, here we can see that there are micro cracks. These micro cracks, they happen during and we can see these things with the traditional night eye. For example, the pro-taper system. But certain ways of strengthening the instrument or modifying the alloy have been advocated. For example, the heat treatment, what we call the post-machining, post-twisting, and we can see that with the high flex systems, for example, the CEM. Here, the heat treatment affects the superelasticity and the shape memory. The M-wire, which is partially in martinistic and pre-martinistic R phase. And this is in the wave 1 system. We get a strong instrument, but it is not really smooth. Twisting the files here, heating, cooling in austenite phase to form what we call the R phase. We're twisting the instrument. That's why we have got slight smooth instrument. Or we can do electropolishing like the race system by FKG. Here, an homogeneous oxide layer is electropolished in the instrument to make it a very smooth instrument. There are many articles that we have done. You can go and read them. They're very interesting. For example, here we used the cyclic fatigue test of wave 1 gold and reciproc blue using different irrigating mediums. We used the sodium hypochlorite gel, and we found that this gel was very harmful to the rotary instruments, and it decreased the cyclic fatigue. Another test, this was done by me and Dr. Lenz from the same college. We did the cyclic fatigue test of Wave 1 Gold Glider with the other types of path files, and we found that this Wave 1 Gold Glider is much, much better, and that has got a lot stronger property with the elasticity, so that it lasts much longer than the other path files. Canal curvatures here, they are very important because the fracture potential of any instrument rotating in a curve, it becomes greater as the angle of the curvature increases and the radius decreases. So that means a very wide smooth curvature of a root is less harmful than a small, very sudden curvature with a decrease in the radius of the cycle. As you can see here, this instrument failed. Why? Because it has got a sudden curvature in the root, and the operator did not operate sequentially to decrease the harmful effect of this curvature. While on the contrary, the mesial root had a more smooth curvature, and it was instrumented and obturated easily. It is found that 33 times more fractures happen in the apical region more than the coronal, and instrument fractures, they were significantly greater in molars than in premolars. We can see here the curvature of the root canal, while here the curvature is very smooth. That's why it fractured here, and this area is very difficult to instrument, much more harder than this root. Here, first of all, we have to start from top, access opening. We have to have a straight line access to the canal. The apical region has to be dealt with very easily. The instrument should not be stressed while entering to the root canal. Elimination of the 2 points of maximum flexure or curvature, and we have to have a better glide path to the apical region. That's why we may consider extending the apical region. I really don't like the minimum access opening, because maybe you're decreasing the removal of the tooth structure, but you're jeopardizing the file, and it may fracture because there isn't a lot of space for the instrument to move about. We have to ensure a patent root canal by the size 6, 8, and 10. For example, this double curvature here, and at the same time, we should not forget we have to use the lubricants. I really like Glide. It's very nice. It decreases the the tension of the instrument entering to very narrow canals. Canal preparation here, it's important that the coronal area of the root canal has to be widened to a certain degree, not too much, but to a certain degree, so that the rotary instrument would enter, and the flaring of the main canal is important so that we can see the apical region clearly and clean it. The coronal triangle, which is very, very harmful to the instruments, has to be our primary goal in our instrumentation. When we use any coronal instrument, for example, the SX of the ProTaper Universal, or for example, the X1 of the ProTaper Next, we have to do the flaring or the what we call brushing technique against this wall, and we have to have have to remove this curvature so that the instrument enters freely to the apical region. This is really the most important thing in instrumentation of a curved canal. This is the primary step, and you will get such a picture. It is very smooth. The orifice is very wide. I can see my orifices very clearly. I can manage my instrumentation to the middle third and the apical third easily. Then it is important that I use any system that I like, but sequentially. If the manufacturer instruction says I have to go X1 for the coronal, then X2 for the middle, then X3, middle and apical here, X3 apical, apical, apical. This sequential order has to be respected by us. We should not bypass any instrument, because if we do, there will be more stress on the instruments and they will fracture. For example, when talking about the wave 1 gold, we use size 10, which has a D0 of 10, ProGlider 16, D0 16, and wave 1 gold primary, which has a D0 of 25. This is very nice, but I personally like to, or I see that the gap between the 16 and 25 is rather a lot. That's why I always use the small wave 1 gold, which is size 20. So you get a very gradual sequential increase from 16, 20, 25. In this case, you will not have any fracture happening to your instruments. Always we have to have the pecking motion. We should not force the instrument inside. Pecking motion is entering the instrument 1, 2, 3 and out, clean, and so on. So the instrument will not be locked in the apical region of the canal. Very, very important that after instrumentation, I have to always look at my file. A file that is full of debris like this, it will not cut if I return it to the root canal. What will happen is that it will rotate in the root canal, and it can't cut, so it will scrape the surface of the root canal, and then it will generate heat and it will fracture. So I always, whenever I place my instrument inside the root canal, for 1 second, 2 seconds, 3 seconds, and I take it out, I have to clean it so that when I return it to the root canal, it will be clean and the flute spaces empty so that they can take more of the debris and cut very efficiently. Irrigation is very important. Sodium hypochlorite has a good lubricant action, and alternate irrigation with sodium hypochlorite and EDTA removes the debris, whether organic or inorganic. The needles, they have to be placed in areas whereby we can clean or remove the debris. So placing the needle in the coronal area or the middle area is not enough. We have to use the side vented needle, and we place it in the apical region as apical as 1 millimeter from the apex. Side vented needle will ensure that the irrigant go sideways laterally and it does not go apically. So this is good and this is not. So the drawbacks of removal of the instruments. This is a thing that happens when I don't think of preventing my fracture. Now I have to deal with the instrument. Either the instrument is so locked in the region and I have to live with it. I obturate on top of it and follow the case. Or I try to remove it and it goes further in the apical region, in the periapical region. Or while trying to remove it, I fracture it, the piece. Or finally, after vigorous ultrasonic action without real knowledge of what I'm doing, possibly there will be perforation. So really it is important that I understand how to prevent the fracture more than how to remove a fractured instrument. So the conclusion by Peter and De Fiori, they stated, first of all, avoid subjecting NiTi rotary instruments to excessive stress. Use these instruments that are less prone to fracture. Follow an instrument use protocol. Assess root canal curvatures radiographically before we start anything and instrument them carefully. Ensure that the endodontic access preparation is adequate with open orifices. Enlarge root canals with fine hand instruments. Set rotational speed and torque at low levels. Use the crown down technique. Irrigate and lubricate root canals during preparation. Manipulate rotary instruments with a pecking or pumping action. If inexperienced, engage in a preclinical training in the use of rotary instruments before tackling this job in a patient. And thank you very much.